Anyway, I will start this brief introduction. My name is Nazareno Pierdicca. I am from Sapienza University of Rome, and I am chairing this modeling in remote sensing technical committee of the IEEE Geoscience Remote Sensing Society. And we are organizing many different webinar. I hope you had also the chance to follow the previous webinar that we had last year. Today we have a new webinar, and I would like to thank Professor Tommaso Isernia. Tommaso is a professor at the Mediterranean University of Reggio, Calabria in Italy. His research work is mainly on electromagnetic electromagnetic field applications, but of course, probably it is not following specifically remote sensing and society and then geoscience, but for sure there is a very close connection between the remote sensing and especially the modeling for remote sensing and in general the electromagnetic theory. So I would like to thank Tommaso for being available to give this a webinar, which is in any case some sort of remote sensing, even not from space, but we can consider this topic very close to remote sensing, and also providing some methodology that could be also transferred to the remote sensing discipline. So I think that I can directly give the floor to Tommaso to start his presentation. Now we have 90 people that are following this webinar. I, of course, thanks a lot all of you for being interested and for attending. The webinar will be recorded, and so it will be made available through the GRSS channel in YouTube. The presentation will last for about, I think, 40 minutes or so, and any question should be raised at the end. You can use the chat, for instance, or you can raise your hand. So at this point, Tommaso, I think we can start.
Thank you.
So the floor is yours.
Thank you very much, Nazareno, for this kind invitation. Thanks indeed to all the attendees for being here in this virtual place, and welcome to this webinar. As you can see from the title, today we want to indicate whether and to what extent one can see through walls and or the subsoil, or at the other end of the chain being invisible. And this is somehow related in my fantasy to superheroes, and we want to understand whether seeing through walls or being invisible like Superman and the invisible girl pretend to do. I'm Tommaso Isernia. Nazareno already said it. I am part of a small group of passionate researchers in Reggio Calabria. Reggio Calabria is the southest part of Italy, just in front of Sicily. So let me come directly to the point. It is pretended that Superman can see through walls and see beyond it and see what happens on the other side. And this fascinated me when I was a teenager. And on the same strip journals, that there was also some advertising. It was a long time ago where it was pretended that by using these special glasses, you could see through clothes. And of course, it was a big fake. But please be careful, because after so many years, if you operate at a millimeter wavelengths and you are at an airport with a setup like the one you're seeing, in the end they can see through your clothes. And of course, the reason here are for security reason, and they could get arms and things like that. So that maybe a new advertising of those glasses would be more successful now. On the other side, at the other end of the problems, that there's someone who wants to spy like Superman, there's some other one which instead pretend to be invisible like Harry Potter, or in some ancient Western mythology, but I guess something similar is present in the Eastern mythology, in the Eastern history. And of course, again, cartoons plays their role with the invisible girl from the Fantastic Four. And so we come to a kind of archetypal scheme where someone wants to see, he wants to see from the other side of the wall, but does not want to be seen. And so let us see if someone wins and which one wins this kind of joke war, let's say. Bad news for all of us, but all of us is already knows that in as far as the frequency for the visible light, for sure you cannot see through walls and you cannot see through bodies. And seeing at the X-ray would not that be so interesting. You just would see bones, and so you also cannot use that part of the spectrum. But at the microwave range and to some extent in the millimeter wave range, you can try to do something. And so let us try to formulate some possible mathematical setting of the problem. Before doing that, in this issue of seeing, we have, let me note, we have some kind of a hierarchy, let me say, of problems, which could go from detection. You just want to understand whether something has changed in your scenario or not. Then you raise your desires, and you also want to understand the obstacle, how far is it, and maybe which angle is it, and maybe still going more and more difficult. Maybe you know your obstacle belongs to a finite to a finite set of elements, and so you can try to classify your obstacle amongst a given set of elements. And then raising again in difficulty, you come to qualitative imaging, where you want to understand the obstacle, you want the shape of the obstacle, you want to identify dimension. Let's say you want to get the shape of the obstacle, and this you could call that qualitative imaging, at least for the community where I come from, which is essentially antennas and propagation, but also I worked a lot with the geoscience and remote sensing community. And things are not yet finished, because there's another still more difficult problem wherein you want to go inside the object. You want to go, for instance, inside the subsoil and understand the internal properties in the subsoil, or maybe you want to make some biomedical imaging in the same way you do with echography, or you do with computer-aided tomography. We need some formulation of the problem. I will try to keep it as simple, as stupid as possible. And in order to write a single couple of equations, I just will write a single couple of equations, and then we go around them and discuss and maybe process them a little bit. We could formulate the problem in a two-dimensional invariant geometry with the non-magnetic obstacle, and also we pretend that we have a set of antennas surrounding the region under test, surrounding the region under test, which can act both as transmitters and receivers. In some cases, we need monochromatic experiments. In other cases, we go time domain or at least multi-frequency. And the idea is this one. We have a set of incident field where RT means the position of the primary source. We have a set of scattered field, that is the fields which are due to the presence of the obstacle. And we want to go back to the so-called contrast function. So the contrast function is a complex quantity, and this complex quantity somehow embeds all the target properties. It encodes all the target property. So that if we are able to find this unknown function, we are able to get the overall scenario, which also includes, of course, the shape and everything we need about that. Let me come to the single couple of equations I will use. And sometimes I will use, some other times we just go by reasoning without equation. And the couple of equations is this one. There's a first equation on the first row where we have our data. Our data are the scattered field as measured in the measurement point Rm and as due to sources located in RT. And in the end, they are the superposition of the effects of some induced current. These are also called contrast sources. This quantity here I'm pointing with my pointer. And of course, GB is nothing else than the Green's function of the scenario. So in the end, our scattered field is some integral operator acting on these contrast sources, on this induced current. And this is the equation which contains the data. We also have another equation, which is called the state equation, which defines what is the total field inside the object. And the total field inside the object is nothing else than the sum of the incident field, that is the field which will be there in the absence of the obstacle, plus the scattered field. Note the two integrals appear formally the same, but the observation domain is different. In order not to go forward with the overall integral, these integrals are synthesized in a formal way by by means of this operator AE and AI, which means the external radiation operator and internal radiation operator. I have an important point here. Maybe someone may be frightened by the concept of operators. Just think in terms of matrices. So if you are frightened from operators, this AE is nothing else than a matrix related to the induced current to the scattered field, and the same holds true for AI. So you can think them in terms of matrices, if you like, if it's more comfortable for you. This is one way to write this equation. Another way to write the same equation is in terms of the so-called contrast sources. And so the couple at the top of the couple of equations at the top of the screen and the couple of equations at the bottom of the screen are essentially equivalent each to the other once one introduces this concept of contrast sources, right? Let me begin to make some comment. And the first comment is that, as you can see, the problem is nonlinear, because in your equation, both the contrast as well as the total field are unknown of your problem, and things do not change if you use the alternative couple of equations, because of it seems that the first equation is linear, but in the end, this is so difficult that you need to know something about the contrast sources. And when you look at the second equation, again, the nonlinearity comes into play. So the inverse problem is nonlinear, and unfortunately, this is not the end of the bad news, because also the problem is as we say, ill-posed. I don't want to define ill-posedness, but the idea here is quite let us keep it simple. In the end, you have a finite number of data, while on the other side, your contrast function has infinite parameters to be determined. So you want to determine something which has infinite number of parameters by means of a finite number of parameters. It's like dealing with an undetermined system of equations, and you know solution is not unique and you cannot invert, and so on and so forth. There's also another comment here. It's not just a question of the number of experiments and measures that you are performing, because ideally you could move continuously your probes and trying to get more and more information. But in the end, it is known that scattered and radiated field have a finite number of degrees of freedom. So in the end, you still come back to a finite number of parameters characterizing your experiments. And this is a large part of theoretical literature on the properties of fields, and who's curious about that maybe may have a look to this reference here. Why nonlinearity is also not a good news. And the reason for that is that when you look for the solution of your problem, maybe you span the space of the contrast function and look around to see which kind of contrast function fits at best your data. But if your problem is non-linear, it means that this cost functional is not quadratic. So it may have many local minima, and this is a problem, because when you use a local optimization problem, depending on the starting point, you can effectively go to your treasure, let me say, to your ground truth. But if your starting point does not lie into this number one region, for instance, it is in the green region, and you go down by means of some steepest descent procedure, then you may end up with a solution. In your mind, you have a solution, but your solution is actually far from the actual ground truth. So you're having a so-called false solution. Well, some of you may immediately make a comment, and the comment will be use global optimization. But remember, as long as you have a low number of unknowns, global optimization can work. But here you may be dealing with maybe 1,000 or even more number of unknowns. And global optimization is affected from the so-called curse of dimensionality. And the problem here is that in order to be actually effective, global optimization procedure have a computational burden which grows exponentially with the number of unknowns. So the effectiveness of global optimization in this case is highly questionable. It's something that in the end will not work. So we have two difficulties: ill-posedness and non-linearity. We have to develop some recipe in order to come out from the problems. Luckily, in any application, in very many applications you're dealing with, in particular, I guess, I'm sure, in the geoscience and remote sensing community, you have a lot of a priori information available. For example, you expect some kind of results, some kind of outcome, so you can choose some convenient starting point for an iterative optimization procedure. Or your information a priori can be such that you reduce the number of unknowns. And if you do that, global optimization becomes viable. And so that's good. Sometimes you can exploit some expected property of the unknown. For example, you may know that your unknown is sparse in some functional space, where sparse means that just a few elements of the representation are different from zero, and you can exploit that. It is nowadays very popular in the inverse problem community, using this compressive sensing, so-called, for sparsity. And also you can make some simple linearization of your equation, which also works out fine. And the second recipe, I put them on the same slide because they overlap somehow each to the other. You can give up your sum of your desires. And so, for instance, rather than for looking for the overall scatterer, you just look for the external shape. And you can be happy maybe with an initial processing which has more than one solution, and then you select the right one later on the basis of some more experiment or processing. So these are quite, I would say, quite intuitive ingredients of some reasonable, simple processing of your data. Let me come immediately with some examples. I tried to put different examples in such a way to keep attention as high as possible. So, for instance, this is with the experimental data produced at Georgia Tech by Professor Scott. And one thing you can do in the framework of this equation is trying to see underground if you are able to see plastic mines. And so you imagine you have a number of antennas positioned at some small height from the ground, and you look for that. Well, if you linearize the equation, which is called the Born approximation, we see it in a moment, and you enforce the sparsity of the unknown, you see that you are able to see that there are obstacles just in the shallow part of the subsurface, which is very interesting, and you can find details in the literature on that. So a linear approximation already can give you information, and that's interesting. On the other side, please note this kind of processing is not really quantitative. So you understand that there is something where you see these spots here, but you cannot say it is a mine or it is something else. So you still need some more processing, some more understanding in order to avoid to explode because you missed a mine, or to say there's a mine and the mine is not there, so you have lost a lot of time and a lot of money. So it works, but you still need improvement. So there's large space for improvements here. This is a second example, which is a simulation of some kind of room, and you have a wall here in the orange part and another wall here, and these are all antennas which are transmitting and receiving. You know the scenario. What you don't know if there's someone inside or not. That's a brutal two-dimensional kind of approximation, and it's in fact from and you want to understand whether you're able to see that there is something. And by using compressive sensing and you recover the equivalent sources, you are able to see that indeed something is here inside, and then you maybe can go on in time and see if this person maybe is moving or not, and things like that. And I also tried to take examples from the Geoscience journal, and in fact, this one is on Geoscience and Remote Sensing Letters. This is still another kind of things that you can do with the relatively simple method. And instrument configuration is the so-called borehole configuration. You dig some holes in the underground, and you put in the holes transmitting and receiving antennas, and you want to see if there is some inhomogeneity there inside. And you see by means of the same method as in the previous slide, one is able to get this kind of things. So you are able to get some imaging, which is essentially a qualitative imaging, but I guess, I'm convinced actually that it can be useful in very many cases. And by making a very brief summary of what we have found up to now, it's surprising that linearization may act as a qualitative imaging tool even outside the expected range of validity. So what I showed with the mines is well outside the expected range of validity, but this notwithstanding, but for precise mathematical reasons we will not go through, one is able to get an image, and the point of view of inverse source is also comes out to be it's a rough one, but it's also an effective one. And in particular in geoscience and remote sensing application, where sometimes you have an uncertain knowledge of the scenario, these methods can be very interesting, and in fact they are widely applied. We have another, then you can change your point of view and make your imaging in terms of so-called indicator function. Indicator function is some kind of function which is supposed to be zero where the object is absent, and instead is one where the object is present. It has a very well-defined understanding from the point of view of physical meaning. And what I'm going to show is some example, some nice results we achieved in an European project which was devoted to technologies for humanitarian demining. And I will skip the processing. The processing is just the solution of a linear system, but I don't want to go through it. And this is the kind of things that one is able at the different frequency. We are using some frequency with shallow penetration in the shallow part of the underground. And you can see that by means of this so-called simple method, one is able again to get the presence of something and to say where it is, and to say it is, and to say which dimension it has. So it's a relevant kind of result. And of course, if you want more information, write us, and I will be happy to suggest reference on all these kind of examples and results that I'm showing here. Up to now, one needs a very large number of transmitting and receiving antenna, which is not so good, but even reducing a lot the number of measurements, one is still able to do something. And this is these are single frequency processing, and you can put together, so you can do a lot of things in this very relevant kind of humanitarian application. Okay, let me move to the second part of presentation, where we go to some not so easy kind of processing. And I want to introduce a concept which has a nice physical interpretation, and let me see if I'm able to get some reasonable description of that. The equations are always the same. We always plan to go around with antennas and so on and so forth. The equations are always the same. I promised that I would have used always the same equations, and I'm keeping my promise up to now. Let us suppose we are in an homogeneous background. We are in a two-dimensional geometry. So the green function here has maybe apparently difficult expression, but it is nothing else than a cylindrical wave emanating from a central point. The equations you see are non-linear. If one could know something about the total field, the equation would become linear. If I know something about the total field, or if I know exactly the total field, the equation will become linear. Let us see if we can do something in this direction. And the idea here is to have some synthetic processing of our data. Sorry that the figure is not centered. I'm sorry about that. And we can do something synthetically. Well, nowadays it's one uses given locutions, and digital twin is a very popular kind of expression nowadays. What I'm going to exploit is not exactly a digital twin. Let me make a little joke. It is a kind of digital cousin of the original data. And let me try to explain what I'm meaning because of that. Well, this is the chain of a single scattering experiment. So you have an incident field. This corresponds to a total field inside your scenario. And this total field, as multiplied for the contrast, give rise to a specific behavior of the scattered field at the measurement point. Let us suppose that we make many of these scattering experiments, and let us suppose that we make some weighted summation of the incident field. So we have a linear superposition of the incident field. We do not do that physically in an hardware fashion. We just do that synthetically, right? And then this incident field, as long as constitutive relationships are linear, will correspond to the same superposition of the total field. And so the scattered field will be the superposition, the same superposition with the same coefficients for the scattered field. Now, why doing that? We are not having no additional experimental measurements, so we have no new information, so that could seem a waste of time, right? And so question marks here. Why are we doing that? And the idea is there. We are still unable, we still are in trouble, but as we have these degrees of freedom on the coefficients of the superposition, we could try to arrange this in such a way to condition, let's say, the total field to obey some kind of behavior. For example, I go directly to the point, if we are particularly good in doing that, we could enforce some kind of focused total field. If we are able to get some kind of focused total field in the virtual experiment, it means it's like we are interrogating a single pixel of our scenario. So this is a kind of synthetic focusing we are looking for. And in fact, this is the idea we have followed, and we have organized virtual experiments in such a way that the scattered field seems to be a cylindrical wave emanating from the pivot point, from the given pivot point that we are using, and then we can use another pivot point and make another virtual experiment, and so on and so forth. So by so doing, we effectively achieve in a large number of cases, not always, unfortunately, which is the reason for this but for at the right side of the slide, we are able to get some focused behavior of the total field, and then we can get some nice, let's say, approximation of the total field, and then we may have a linear approximation of the equation that we call the virtual experiments linear inversion method. But we can do that in free space, but we can do that also in scenarios different from free space. We just look for perturbation with respect to the known part of a scenario, which we call the distorted virtual experiments method. And then we can do something else. We can iterate the process. We start with a first evaluation of our scenario, then the estimated scenario becomes the background of the next step of our processing. For maybe some of you has heard or studied the so-called distorted Born iterative method, and so one can do the same with this kind of virtual experiments, and one can progressively improve its processing. And we are very happy about all of these. And these are some kind of reconstruction that one is able to do on some lab experiments, which are a kind of benchmark for all of us involved in this kind of inverse scattering stuff. And the value of this reconstruction is that up to that moment, it seemed that obstacles of that kind was not possible to achieve the reconstruction by means of deterministic iterative procedure, and instead we are able to do that at frequency as low as 4 gigahertz. And this is with the regularization, final regularization based on truncated singular decomposition. This is instead the results achieved by compressive sensing kind of regularization. I just want to say a last thing about this virtual experiment stuff. I have insisted, I've put focus on the fact that one is able to get some kind of localization of the internal fields. Well, to make a long story short, the fact that you are, in the end, you are interrogating locally your object, it means that you can focus at different moments at different parts of your object. And to make a long story short, we were able to come to reconduce the overall problem to a diagonal system of third-degree algebraic equations. But third-degree algebraic equations admit a closed form solution. So pivot point by pivot point, we are able to get an estimation of what's happening, as long as the focusing mechanisms work, of course, which is very large set of cases, but actually not always. And in the end, we come to some kind of very polite reconstruction, which are also very, very fast. So this is the part which is also of interest. for real-time applications, which are always behind the corner in all engineering application. So, as a summary of the third part, the virtual experiments allow to overcome part of the difficulties by leveraging focusing total field. I say part because not always one is able to get this kind of focused behavior. We have also worked on a further recipe I want to go through briefly before going to conclusion and maybe invisibility if there is time for that. This is the standard formulation. As promised, they are always the same couple of equations. And suppose we are in an homogeneous background with this expression for the green function. This is an Henkel function, but indeed it is a cylindrical wave. Well, what one can do is doing some kind of formal inversion of the second equation and insert in the first equation above. You cannot do the reverse because the first one is so severely ill-posed that you cannot do anything with that. But if you play this action of formally inverting the second equation and substituting into the first one, you come up with this expression. Now, as if this quantity is sufficiently low in mathematical terms, you say that the norm of this quantity is less than 1, then you can play, you can expand, you can have the so-called Neumann series of this inversion, and you have a polynomial relationship describing the scattered field as a function of the contrast. And why this is important. Let us see what happens. If this norm is not only less than 1, but is much less than 1, then you can approximate this term with the identity. And then it means that the total field can be well approximated by the incident field, so the problem becomes linear, and the cost function will be a well-behaved hyperparabola, and you can go directly to the bottom of this hyperparabola and find your solution. If this norm grows a little bit, then maybe you need 2 terms in this expansion. And so the relationship amongst the data and the unknown becomes quadratic. And then the cost functional becomes a little bit more harsh. And in the end, you have this kind of scenario. If the norm is very low, everything works fine. If the norm is a little bit higher, your cost functional is still may be treatable somehow. If these norms grows more and more, then it becomes a nightmare because you have very many local minima and you don't know how to deal with that. So this quantity plays a role in this kind of stuff. So one possible idea is to reason about that. We define that as the measure of the degree of nonlinearity, and the idea is that by working on the equations, you can arrive to formulations which are much easier and let's say less non-linear to be solved. And just make an example because time is running up. Let us suppose we are in a lossy media. I can elaborate a little bit this the original integral operator, and because of the fact that the green integral has a singularity while the second one has not anymore a singularity, one can say that the first term is dominant with respect to the second one, and one plays with this equation can write in a different way the initial equations. They are always the same, but they are somehow changed, a little bit changed. And in the end, one comes to the same kind of equations as in the usual homogeneous medium. So the same kind of reasoning that one has made above, one can do exactly the same below. And so the nonlinearity is, the degree of nonlinearity is related to the norm of this quantity. And you can show that in lossy media, the norm of this quantity is much less than the norm of the homologous term in the usual equation. And so if you choose in a lossy media, you choose the right model and you go into your nonlinear model, this is the ground truth that you would like to recover. And you see, with the usual model, you get trapped into a local minimum, into a false solution. With the new model, you are instead able to do much more and to get your final results. And you can do that for subsurface also. And this is the kind of results one achieve with the new model as compared to the old model. And so by reasoning on the model, you can do a lot of things. And you have many other possible reformulation, and I would be glad to give more details to the ones which are eventually interested in such a kind of things. Of course, you can mix up the different recipes to get, which are not anymore recipes, maybe they are ingredients, and with these ingredients and basic recipe, you can go to more sophisticated preparation. For instance, this is a last result from our side, one reformulation, and allows to get the exact reconstruction of the shape, even in case for with non-convex subject. But there's no time to go inside that. There's something I cannot skip, and something which I cannot skip is that besides this, let's say, old-fashioned way of proceeding, you can also use, of course, machine learning, deep learning techniques. This is a very hot tool, and one could open a wide debate on that. Maybe Professor Pierdicca, maybe if you have not already done it, maybe this is a hot topic which deserves some discussion. In my understanding, it is a form of enforcing a priori information. The part of training puts into the process a priori information which allows you to defeat ilposeness, to defeat non-linearity, and one can make a lot of things with that. As you all know, the claim with deep learning is that it goes very fast to the solution, and I agree with that, except with for a comment. They resemble highways, they go very fast to the final point, but you have to build the infrastructure first, and this may be costly, and you can have to decide which is the infrastructure, and then you have a question of whether the infrastructure actually reach the destination that it was that corresponds to the ground truth. So there are very many things that could be discussed. I won't discuss this slide. I just leave it for the registration in case one wants to debate about it. Let me come to the conclusion, at least for the part of seeing through story, and my understanding, my conclusion is that someone look inside objects or even beyond them, and also multi-frequency, we have not used that very much, but can be useful. But of course, this is not a seeing through in the Superman or Supergirl way of thinking, because you have a trade-off by penetration and resolution. In order to penetrate, you have to lower the frequency, but this means that the wavelength increases, and so your resolution becomes poorer and poorer. This is an active kind of sensing, and it's a multi-view experiments. In the Superman sees from two eyes, which is some kind of my system, but with just two elements, you need much more of that. And so, in the end, you can do a lot, but you cannot see as Superman. I don't know if I have time for the other part of the story, and the other part of the story is whether one can render itself invisible, like in Harry Potter. I go very fast because time for questions should be left. And the idea is that the problem of invisibility could also be put in terms of scattering, where the requirement here, there are not any more measures, there are instead prescription, and the prescription would be that for any couple source observation, the scattered field has to be zero. And so you can somehow design your invisibility cloak and become invisible, as Harry Potter does. And these are just a simple example. You see in the example, you see an uncovered object, and of course you see a large scattered field. If you cover it in some clever way, if you in the second figure here, you have some kind of plane wave which is coming from below, and you see the total field continues to appear as an unperturbed plane wave if you do correctly your things. And you can play with scattering and invisibility. So scattering could be useful for invisibility, besides being useful for imaging, for seeing through walls and seeing in the underground. So this kind of mantles have been built and so on and so forth. That no time for that. These are some kind of let's say advertising results, because these are you can do less than that, unfortunately. So at the end of the overall story, I'm sorry I've used more time than I was allowed. I would say Superman is able to better and better look through walls, but the invisible girl is able to be more and more invisible, let me say. So the archetypical situation we started from stays there and will continue likely to be there. And there's a lot of funny things useful in many applications besides cartoons, which can be done. And it's we enjoy very much our activities on this subject. Who wants, I can send the presentation with a number of elements. And I stop here, and I thank you very much for your attention. And again, I apologize, I was maybe a little bit late. Thank you so much.
Thank you to you, Tommaso. Very nice presentation, and I guess you can help me to become like a Superman. So I think that we have some time for question. Just about your comment about the use of of machine learning. I would like to say to the audience that as modeling remote sensing technical committee, we have recently set up a new working group that is about a physical model informed neural network. As from one side, the neural network, the machine learning, data-driven approach can help modeling people to understand better the relationship between data. And on the other side, I think that the physical model can help people that are doing retrieval using a data-driven approach to account only for constraint and avoid let's say, error when the data set is not enough to get a robust model. So we have some question. There was a question from the very beginning of Stefan Barger that would like to know something more about the FP7 European project D-Box. I don't know, probably if you have Tommaso.
Yeah, that project closed some time ago, I think 5 or 6 years ago, but the idea from the European community was developed a vast range of very different technologies which goes from training of dogs to chemical sensors to radio frequency and microwave tools in order to do the best, in order to try to track metallic and better plastic mines. I can find details of that old project. The project was supposed to have a continuation, but I was not involved in that continuation, or maybe there has not been a continuation. But I can find the details and find it. It was a very large project with very many. With many nations involved, and you have sites for testing the different technologies, even in a joint faction. That there was a path for drones as well. It was an interesting and productive project. I should have the booklet somehow, and I can provide if desired.
Okay, thank you. Any other question? I see many people that are... Okay, so I've seen another question now. According to the linearization using Born approximation, can you suggest any additional methods for improvement?
Yes. Some of the improvements have been throughout the presentation. So the idea in the Born approximation is simply to approximate the total field with the incident one. One of the recipe I've shown, that the one with the virtual experiment, is already a kind of improvement, because still one is now approximating the in that framework, one is approximating the total field with the incident field plus an estimation of the scattered field. More precisely, the approximation of the scattered field is, let's say, the back propagation of the cylindrical wave back to the pivot point. So this is an approximation different from the Born one. And then, of course, one can have the so-called distorted Born approximation, where your linearization is not anymore in a void scenario or in an homogeneous scenario, but takes into account your a priori knowledge of the scenario, and this is known as the distorted Born approximation. And then in the literature you have this kind also very popular distorted Born iterated approximation, where you play with the subsequent linear approximation, and this is somehow equivalent to solving in an iterative fashion the original nonlinear problem. One as far linearization are concerned, you always have to use all you know about that. So if you know something about the scenario, use that for the green function, or use that in the initial point of your iterative procedure, and so on and so forth. So everything should be inserted because problem is mathematically very hard. I don't know if I answered, but I tried.
Okay, another question. I'm not sure I have completely understood from Srimadi. Is there any specific range for the microwave imaging to do machine learning, deep learning, and even to do the see through things? Not clear to me what kind of range was the question dealing with.
Well, I will interpret it in a general sense. So the application of machine learning to seeing through walls and the kind of limitation one has. So one limitation is, of course, in the setup of frequencies. I tried to say something in the ending part. So you can use microwave if you want to go maybe for mines or things like that. You can use lower frequency when you want to go for oil exploration. When you want to go through clouds, you can use millimeter waves. So the choice of frequency is related to that. And that is a kind of, let's say, physical construction, physical constraints. Then, as far as machine learning is concerned, you have some kind of, let's say, mathematical maybe or methodological constraints. And the point is you have to know something about what you are looking for, and then you have to train that. And if your ground truth is very different from the training, then I have doubts that it will work. And another limitation is maybe on how many numerical experiments you should do in order to have a proper training. And also the setup could not correspond to your simulation, so that it would be better to have a training with measured data. But having a training with measured data, you need a lot of training, a lot of data to train properly, and this becomes another limitation. If you want to train directly with measured data, that could become a nightmare unless you have very fast, very precise forward modeling. So there's a lot of stuff to be deepened. And I guess there's also a lot of stuff for our people, for all the people interested in such stuff, because you need modeling of your scenario, you need modeling of your setup, and so that there's a lot of room for everybody, for the forward part, for the inverse part. That there's a lot to be done, but I mean, it's fascinating. I still want to buy those glasses, let me say.
Actually, as a MERS technical committee, we suggested and proposed a session at IGARS, next IGARS in Brisbane, about physical model informed machine learning for remote sensing. Let's say the time, there is still time for submitting papers, so I invite you, all of the attendees, to do it if they are interested and they are working on this subject.
In my view, physics should definitely enter this stuff, because it will be a pity all this understanding we have acquired will get lost in some kind of black box. I hate black boxes. Yeah.
I fully agree. Okay, so any other question from the audience? I have one very quickly, Tommaso. In all these problems, you have your unknown is the contrast function. That is a sort of deterministic description of the object. In remote sensing, many times you have a sort of random media, so you cannot describe it as a deterministic dielectric constant as function of the space and the time. So, do you know about how the thing that you have just very well explained in this webinar could be also used in the methodology in a framework in which the media is not deterministic, is a forest, is a random surface of the sea?
This is a very good question, which opens still more room. As a first part of my reply, I will say that there are a number of colleagues, including the colleagues from Trento, which you know, Andrea Massa and others, which put this problem in some kind of probabilistic fashion and kind of Bayesian a posteriori something. And this is already something which can be useful to go towards the probabilistic kind of understanding. A second way could be the fact that in the end, you also have to deal with some kind of description, which will not be anymore, let's say, a deterministic function as the contrast, but maybe a probability map or some averaged quantity or things like that, and everything should be rephrased, let's say, in terms of these probabilistic quantities. I've never worked on that, but it seems to me that something could be done, and that seems to be a fascinating area. So I have not recipes, but I see some path to be explored.
Okay, fine. So finally, I think that this is the last concluding question. That is, how close are we to achieving superhero-like abilities?
I've got some secret for that, but in the meanwhile, I will unfork my magic glasses, and this is a secret for all of you. No, I'm joking. It's a continuous. There are physical bounds. You can never reach Superman abilities. So there are physical bounds. As long as you can see from the trade-off amongst penetration and depth of penetration and resolution, I think that the processing part is making wonderful advances, and aided by machine learning, maybe can also be real time. But be careful, this kind of seeing through is not just two eyes. You need different antennas, and you need multi-view, you need a lot of things, but as long as you do not violate physical bounds, I mean, you can never look through walls at visible light. As long as you do not violate it, I am optimistic. You can overcome impulsiveness. You can overcome by means of regularization. You can overcome non-linearity by means of clever schemes. So that you can do. But at visible light, unfortunately, I can buy whatever couple of glasses, but I won't be able.
Apart from your glasses, your
Okay,
personal
apart
glasses.
from my
Okay.
magic glasses. Okay.
Okay, so Tommaso, thank you very much for this very interesting webinar. Thank you to all the people that attended this webinar. I hope that they are satisfied that they learned something interesting for their job. And I will wait
Thank
all
you
of
from
you
my
for.
side. Thank you
Uh,
from my side to you and to all the attendees. Thanks
okay,
again.
so and
Feel free to get in touch, everybody.
yes, I think you have the all the reference and coordinates to reach Professor Tommaso in case you are interested in further information. So again, bye everyone. Bye bye.